let's continue, and this is the first part of graph connection of Laplacian and the vector diffusion map discussion. And the literature for today will be these 3 papers, which you can check details if needed. So, what do we want today? Today, we want to talk about some topological properties of a manifold, and we will focus on the orientation. Okay, so what is the orientation? So you may recall that there are several different manifolds that are not orientable. And actually the bundle structure can help us to figure out those kind of topological features. For example, what we want is to detect orientability from a point cloud sampled from a manifold. Examples include Mobius band, which you all know, and this is some kind of a piece of paper, right? And you can, if you wrap it, this is a cylinder, but if you when you wrap it, you just flip. Okay, and then after flip, I just tap it. Tap it. Okay. Okay, then you see, this is the Mobius band, and the Mobius band, as you can see, it is not orientable in the following sense. If you start from this point, then you go, right? You go. Now, our pen is always on the north part, perpendicular to the band, right? If I go, and I'm just going, right? And at this point, look, this is where I start, right? But now the point is on the other side. So what is the orientation? Is this the positive side or this is the positive side? And you can continue and you will go back to the original point. So this is kind of something that you can utilize to design this kind of ring. It's kind of interesting. Okay, and well, love never going empty. This is, well, you understand what it means in the future. Okay, and there are some more higher dimensional another orientable manifolds. For example, these are real projective plane RP2, and those are the 3-dimensional realization, or Klein-Bartel, which is the 3-dimensional implementation. And what is a Klein-Bartel? Klein-Bartel, you can view it as you have this. You say this is a cylinder, right? This is a cylinder. This kind of tunnel, and if you just bend it and map them, this is torus, right? And now, if I say that I want this direction to match, this is direction, upside direction, okay? And I want to map this, but not the up direction. If I want to map the up direction, that is the torus. I want to map the down direction. Okay, I want to map this one with this one. And how can you do it? Right? When you want to do it, you put them together, and you see, when you put them together, their direction are opposite. Right? Then what you can do is you try very hard, but no matter what you do, you cannot do it because the direction is always opposite. The only thing you can do is what? You may kind of dig a hole, right? If you are allowed to dig a hole, you dig a hole, and now you insert this one into it. Then you see, okay, you can measure it. And this is the Klein-Bartel realization here. But obviously, when you really want to generate a manifold, you cannot use scissor to cut one piece out, right? So the only way you can realize this kind of cut and insertion is via high-dimensional space. So Klein-Bartel can only be embedded in 4-dimensional space. And RP2 is also can only be embedded in 4-dimensional space. And there will be a lot of interesting topological features that you can study, but we will not go into details. You can go to characteristic class textbooks for more details. Okay, so what we want is, as I said, I give you a point cloud. I want to detect if the associated manifold is orientable or not. So how to do it? First, recall the parallel transport estimator that we discussed in the 4th lecture. What you do is, first, you run local PCA at different points, and from local PCA, you can estimate a basis of the tangent space. That is, you obtain an estimated point on the frame bundle. And you can then try to do the minimization of this function. If BIT, BJ, and abstracted by O. And what is BIT? BIT in general is a P by D matrix. That is, you have D vectors in P-dimensional space that is determined by local PCA. And please go to lecture 4 for details. And now you have BIT times BJ. That is actually trying to project the basis you get in BI to the basis of BJ. And this projection is actually plays the role of rotation. But in general, BIT, BJ is not orthogonal because you have curvature. So the projection may not be orthogonal, but if you do a fitting, you fit O, an orthogonal map, an orthogonal group into BIT, BJ, then this OIJ, you can show that it is an estimator of the parallel transport combined with the frame bundle samples. Okay, and what you can to solve it, you can just use SVD and determine OIJ as U V transpose. That is the algorithm. Easy. Okay, so you can get an estimate of parallel transport. So the algorithm to detect orientability is the following, which is kind of simple. What you do is you now construct an n by n matrix, which is called Z, which is Z is D inverse Z. And this Z matrix is actually Wij. Wij is the same affinity from diffusion map. Now the only difference is you have determinant of Oj. And because Oj is what? It is an orthogonal group. So determinant of Oj will be plus or minus 1. So you see, this Z matrix is no longer like what we had before, like an affinity matrix. It is an affinity matrix combined with plus minus 1. And this plus minus 1, again, comes from determinant. And you have the Dii, Wij. And then what we do is you just evaluate the eigen decomposition and find eigenvalues for eigen decomposition. And now you take the top eigenvector, you evaluate the sign of each one as Zi hat, which is this guy. That will give you some kind of the estimator of what we have interest. Fine. Now, before continuing, take a look at this formula. Doesn't it rings the bell? It looks very much like what we get before as graph connection Laplacian. And if you remember in graph connection Laplacian, what we did before was we consider the group action and attach it to the affinity. And we will see later that this determinant of Oj is actually the group action we have interest in, and it is an orientation bundle. Okay, so technically we are using already the principal bundle idea to handle everything. But the principle of the language will be discussed in the future, not yet. But now, overall, that is what we will utilize. And now we just plot the result of the top eigenvector, and you can see that that will be the distribution of the top eigenvector, and you see If it is S2 is clean, then you get either positive or negative, which just tells you that because when you run local PCA, at each point, the orientation can be positive or negative, but you will not get anything confused, even if the data is noisy. But if you now run the algorithm on Klein-Bartle or RP2, then you see it is kind of everywhere. Why? Because the top eigenvector cannot identify what's really going on. There is no orientation, so everything can happen. So from this distribution of the top eigenvector, we can use it to determine if a manifold is orientable or not. That is, if you have two very clean, clear separation, then it's orientable. Otherwise, it is not. Okay, so this allows us to further understand the database. In particular, understand the topology of the data set. But how does it work? As I briefly mentioned before, it is related to a principal bundle or something, orientation bundle, but let's forget about those complicated language. Let's just look at this simple explanation. So let's take a diagonal matrix called gamma. Okay, and suppose gamma is the orientation of the tangents of the basis of the tangent space. That is, suppose OI is the basis, its determinant is either positive 1 or negative 1 of the tangent space. We want to recover. And this is why it's positive or negative, as I mentioned, because when we run local PCA, we don't know if positive or negative. Then what we have is Z matrix we discussed before, or I use Z1. Let me check. Or I use Z1. This is Z. This is just curl Z, okay? Yeah. No, sorry, this is curl Z, just curl Z. Okay? But the curl Z is actually D inverse W. This is diffusion map. And you conjugate this down. So by taking this into account, you will immediately see this. So this is a relationship we obtain. And now, if you evaluate the top eigenvector, this is E inverse W top eigenvector, then the VIZ, the top eigenvector of Z, will be gamma times this guy. Okay, so VIZ is the orientability of the tangent space at xj. That is what it tells you. And again, this can be discussed under the framework of principal bundle, and we will talk about that framework later. Very good. So now we find a way, we have a way and an explanation that why we can discover or understand the orientation. Next, we want to discuss another thing called recover the double coupling. How to recover a double coupling. So, if you remember, we had this Mobius span, right? Now, I will play a game with you. That is, I will use the scissor and cut it. And see what you get. Just cut it, okay? Now, I will cut it according to the line that the trajectory I went. Okay, I just cut it. Oops. Okay, continue to cut. Okay, now cut in this direction. Okay, whatever, there's no difference in cutting. So I cut. Okay, finally, I'm here. Cut. Now you see what I get. Uh-oh. This becomes, okay. Rotate, okay, what is, that's not even, hold on. Whatever, this becomes orientable. Okay, so why is orientable? You will see that if now I go from this direction, right, I go. You see, I go. Right, keep going. I don't. Okay, and at some point, soon, you see, okay, it's here. You see, I come back to the original point. So you get an orientable cover, and this is an orientable, technically double covering of the Mobius band. So this is a kind of a realization. Well, okay, got confused. But anyways, you can patch it back. Okay, and you see this is the double covering of the Mobius band. Okay, whatever. Okay, so that is also the theorem that you learn from differential geometry, that any non-orientable manifold, you can find a double orientable cover of it. And this is the example for the Mobius band. And its double covering is C. And how to do so? The technical idea is try to construct n virtual points called Z n plus I, which is the Z2xi, which means it is the flip, or some other ghost point associated with it that reflects the double cover. Okay, so that we can patch all the patches together so that we generate an orientable manifold, double cover. So we view those endpoints ghost, and we do not need to represent them or try to find them. No, we don't. Instead, we use this idea to construct a diffusion map. Okay, and this idea has other applications. We will discuss it in the future lecture. We build up, for example, Z tilde, which is Z minus Z minus Z. Look, this is a very beautiful matrix with symmetry, right? And it is a 2n by 2n matrix. And you will see that this guy actually is the affinity matrix on the orientable double cover. And what you can say is, by this construction, you have all this kind of relationship. Because over here, this is minus, right? And why minus? Because this minus comes from xi minus z2xj. And this z2xj is here, which is the virtual point. So this is kind of assuming the existence of z2xj, and we get the affinity. And this affinity, with this affinity, you can run diffusion map. And because of positive minus, positive sign, only the R function will survive. And what you can say is, asymptotically, in a continuous setup, it is associated with this integral kernel. And this integral kernel will allow us to get the desired Laplace Beltrami operator and recover the double covering. So that is the overall theoretical idea underlying this ghost point assistant recovery of the orientable double cover. Okay, and the theoretical fact is the following. If I give a smooth connected n-dimensional manifold, and it is orientable, if and only if what, you can find a section on the orientable bundle, which is the n exterior derivative form. And this form is spatial, that it is non-zero everywhere. That is what I showed you, right? You have, if it's Mobius band and you go, then it will become ups. So if you want to get something that is continuous, then you must have some place that is zero. Otherwise, you cannot go from this direction to this direction. Okay? And this is kind of the overall idea and the theory underlying this algorithm. And this is the bundle that we are working with, which is dimension 1. You know this exterior derivative, exterior power of the cotangent bundle. This is dimension 1. So what you have is actually a non-trivial bundle if the manifold is non-oriented. And this is the result. If you run RP2 and you run the embedding, you get S2. Because the two-dimensional sphere is an orientable double covering of the RP2, and the torus is the orientable double covering of manifold, and the Mobius band, as I told you, is a C. So you can do some homework to reproduce this result, which is kind of interesting, I think. Okay, and Klein-Bartle is kind of interesting. For example, people have found its application in natural images. For example, they said that if I give you a natural image and all the small patches, actually there is a Klein-Bartle structure in it. And this is Gunnar Carlson, which is my postdoc mentor, who saved me. Okay, and this is his current work, trying to use, although I'm not really a big fan of deep learning, but he used combine this Klein-Bartle information to design convolutional layers for deep learning. And I think that is kind of very interesting direction to think. That is, there's always some topology or some shapes or some spatial behavior in the data that we should respect. And what they say here is, if we respect it, then we can do something better. Okay. And the graph connection Laplacian is also related to synchronization. And this is the main paper that is related to this direction, kind of theoretical paper related to the synchronization. To understand synchronization, you can recall this expansion. And this is from a general graph connection Laplacian framework without any manifold, just simply synchronization. If we are talking about manifold, then we know that connection Laplacian's type eigenvector, if it is 0, then top eigenvalue, the smallest eigenvalue is associated with the most parallel vector fields. And if the top or the smallest eigenvalue of connection Laplacian is 0, then that is purely parallel. So those we all know, but what about the general case? So this is D minus S is D times C. C is the connection Laplacian, normalized connection Laplacian, graph connection Laplacian. And if you do the expansion, that is what you get. And we have had this expansion before. Now, if you look at this quantity, what does it tell you? It is trying to tell you that you are trying to compare V I and the V J. And what is V? V is a vector. It's a vector field in is a spherical valued function defined on the vertex. Okay, and if you take a look at what it means that if you want to evaluate the vector value over I and the vector value over J, then you want to respect the connection and evaluate their distance. That is what it tells you. And suppose this guy is 0, totally 0. What does it mean? It means that Vi is equivalent to Gij Vj, which means V respects Gij and is constant. It is constant respecting Gij, and that is what it means by synchronized. Or this is it's called a synchronized vector. But if you look at this guy, V is a spherical sphere-valued vector field on V, and you want to optimize this function. It is actually quite difficult. So, in general, we can just consider relaxation. Because if you define this quantity as the frustration of synchronization, then this optimization is difficult to realize because this is SD minus 1. So what you do is you simply relax it to evaluate this is RD, just RD, and then this is graph connection Laplacian. And you try to find the minimal eigenvalues. And the main theory in this paper was they established this triggers type inequality, saying that the eta g is actually well controlled by the eigenvalue of the graph connection Laplacian, but you have to do normalization by graph Laplacian. And so it gives you a theoretical guarantee of what we apply graph connection Laplacian to find the most parallel vector field in the general setting. And there will be some more applications, as I mentioned, and we will discuss them in the future lectures.